In this example, we want to graph g of x is equal to x squared minus 4. So we know because it's an x squared graph that it's a parabola, and the minus 4 is causing a shift down 4. So the vertex of our parabola will be at 0, negative 4. And we could do a little bit of algebra to find the x-intercepts, solving 0 equals x squared minus 4. And that would allow us to see that our x-intercepts will be positive and negative 2. So our parabola opens up and has a rough sketch like this one. Now, on the same coordinate plane in a different color, we want to go ahead and graph the absolute value of x squared minus 4. So it's important to understand when we have the absolute value, no matter what value you're inputting for x, the output of this function is always positive due to the absolute value. So graphically, that means that the portion of the graph that lies below the x-axis, which would be this portion of the graph here, that's below the x-axis, this portion of the graph is going to get reflected across the x-axis because the y values will end up being positive. So we can use the original parabola to understand that the bottom portion of the parabola will get reflected. So the y-intercept, which used to be at negative 4, will be at positive 4. And that portion of the parabola reflects across the x-axis, but then the other pieces, in other words, the right-hand piece where x is greater than 2, and the left-hand piece here where x is less than negative 2, those pieces stay the same because their y values are currently positive already. So the result is kind of this funky W-shaped graph. What I have in red is the absolute value of x squared minus 4. And now we want to write an equation, a piecewise function, for the absolute value of x squared minus 4. So if you can realize that the first portion of this graph, I'll highlight here, this first portion of the graph, this was the same as the original parabola, x squared minus 4. And we only want that portion if the x values are less than negative 2. However, the middle portion here, that was the piece of the parabola that was reflected across the x-axis. So that means we will be multiplying the x squared minus 4 function by a negative. So you could write that either as a negative quantity, x squared minus 4, to indicate the reflection using that negative, or you could go ahead and distribute that negative throughout, which would leave us with negative x squared plus 4. And that's going to be for x values that are in between negative 2 and positive 2. So negative 2 is less than or equal to x, is less than or equal to positive 2. And we're including both negative 2 and 2 here because these are actually coordinates on the original graph where those corners occur. And then finally, the far right-hand portion of this graph here, that is the same as the original parabola, x squared minus 4, and that is only for x values that are greater than 2. Now, for the derivative, we'll go ahead and create a piecewise function for the derivative as well. And we'll use our power rule to compute the derivative of each piece. So starting with the derivative of x squared minus 4, the derivative of x squared is 2x. The derivative of negative 4, a constant, would be 0. And that's only if x is less than negative 2. Moving on to the middle piece, negative x squared plus 4. The derivative would be negative 2x. However, we recognize that we have two corners on this graph. There's a corner at negative 2 and a corner at positive 2, and the derivative does not exist at these corners. Therefore, I have to be really careful when I included negative 2 and positive 2 in the original function. I am not going to include those values in the derivative. So this is going to be if negative 2 is less than x is less than 2. Again, I do not include negative 2 or positive 2 in the derivative because there are corners on the original function at those points. And derivatives don't exist at a corner. And then the last piece is the x squared minus 4 again, whose derivative is 2x. And that will be if x is greater than 2. So part D, determine the interval or intervals where f of x is differentiable. Since we have two corners, we recognize that the function is not differentiable at those two corners, but it is differentiable everywhere else. So this function would be differentiable from negative infinity to negative 2, all the values in between negative 2 and 2, and then all the values larger than 2, which would be from 2 to infinity.